All right. For starters, opportunity for some extra credit. We like extra credit. So I'll give you. It'll be 10 points on the final exam. That actually it's equivalent to 10 points on the midterm. The reason I'm doing it on the final is because some of you will have your midterm replaced by your final exam score, so it's actually double dipping. Okay, so that means if you get 100 in the final, you'll get 110 in the final, which then will replace your midterm with a 110. So big points, big points. Okay, now you want to hear what you have to do for the How many of you are willing to give up a kidney? All right.
We got 70 on the midterm, and we got 60 on the final, so we can use 10 points on the midterm.
Doing some out there casing.
Okay, so if you, let's see, you got a, well, no, it won't. So you got a what on the midterms? You go 70 on the midterm.
Yeah, if we got 70 on midterm, so the final, we got 60, so can we use 10 points on the midterm?
Well, then it won't make a difference. You'll replace your 70 with a 70.
No, on the midterm, so that means the midterm got 70, we use 10 points, that means 80.
But the numbers should be the same because you're not going to be replacing it. Yeah, it works. It's in your benefit to have it on the final. Right? Does that make sense?
Yeah.
Yeah. It's worth more percent because you can help yourself boost your midterm grade. But even if you don't boost your midterm grade, the percent it's worth is the same on both. So we have our first. We're going to start doing this annually. We have a hackathon that we're doing here on campus.
November 12th.
It's November 12th, which is a week from this Saturday, right? Does that sound right? And that's at 8 a.m. Until probably 5 p.m. is kind of the thought time. So if you participate in that, you'll get the free bonus.
Can we put that a little early if we have to?
If you have to, yeah. So if you can come for a good chunk of it, but you got to work in the effort.
Like cut it 3 or something, 3 or 4.
That's okay. You'll get your points.
Why don't we get
Participate from home?
Huh?
Can I participate from home?
No.
No.
Well, got to be there.
I think we can do to help leading into it if we have to be on for work that weekend.
Yeah, cause I have to work on Saturday too.
Or is it the process
Sucks
now?
to suck.
No.
I gotta say.
Good luck.
See, we're really trying to buy attendance. That's what it comes down to.
What if I convince other people to go? Because I can't be there.
Well, who's the other people?
Freshmen. Great, so now my team's gonna be 3 freshmen.
Well, no, that's okay. So let me think. Let's see is there an equivalent bribe? Okay, because I'm giving this offer in my other class too, in 250, my other undergrad class. So for those of you who are in both, you can double dip. So if you were to convince somebody else to come in your place, it would have to be somebody who wouldn't be coming anyways from one of their other classes. It's like you couldn't talk to one of my 250 students. See what I'm saying?
Yep.
So a non-CS major.
Oh, no, we want
someone
CS
that's not
majors.
getting credit from Lippman.
Yeah, they can't be getting credit otherwise. They would have to be somebody who wouldn't be there otherwise. So if you can find a person who wouldn't be there otherwise to attend in your honor, okay, they must be a CS or an IT person, then I'll give you the points.
Now, wait a second. If I want to sell if I don't need the 10 points that badly, can I sell my honorary position to Josh so he can say I'm going in his honor? He gets
No, because you have the opportunity to get points for my
So I
class.
wouldn't. I would forego those points and then they would go to Josh.
No. In fact, if you do that, you'll lose 30 points.
I'm trying to wheel and deal here.
All right, so if you absolutely can't reschedule a work schedule or something like that, if you can get somebody to come in your honor who's a computer science or an IT major or minor, or I guess who has some sort of interest in programming or something like that, somebody who would be useful at some level. I mean, they don't have to be strong because we're going to organize the groups to have a stronger person and a weaker people. But I don't want you to get somebody like from nursing who has like zero background or interest in programming to say, look, I need you to show up and just say you're there for me. Okay. It's got to be like a legit person. all right, who wouldn't be getting credit otherwise.
People aren't, they're not people.
No, if you, how many of you know old Alex? Old Alex used to be a nursing major. Yeah, then he graduated. So I mean, so if you want to find a nursing major who's also interested in simulation or something like that, who's done a little bit of something so they can contribute, I'm okay with that. It doesn't have to be a CS major or minor, but it's got to be.
Outside of school.
I guess I'm okay with that too.
Oh, okay. So, I have a friend, that interested on the computer science, and the couple said I was want to interest to get this order.
Okay, well, but you're going to come anyways, right?
Yeah.
And you're going to bring an extra person.
Yeah.
So then you'll be in my good graces. Because in that situation, if there's like a borderline situation towards at the end of the semester where I have to make a call between like a B plus and an A minus or something, I might flip the coin a couple times till it comes up heads. You just never know. All right, so that's a week from this Saturday. What I need you to do as soon as possible so that I can keep tabs of it, and also Professor Locklear needs it as well. You need to email Professor Josh Locklear as soon as possible, because we were supposed to have everybody signed up by, I think, yesterday, but we didn't. We talked about it today, so he's cool with it, so he's expecting emails. So email him as soon as possible and carbon copy me on it, so I can mark you down as expected, which means that I can then punish you if you don't show up. Okay. What's this carbon?
CC.
Yeah. Really? Did you even know that's what it stood for?
Yeah, of course.
Do you know what BCC stands for?
Bigger carbon copy.
Do you really not know what it stands for?
Couldn't tell you. No, I don't think so.
Are you,
Beta carbon
Points,
copy.
the points, huh?
Behind carbon copy.
what is it, Trey?
Blind carbon.
Blind carbon copy.
I should have known that. I mean, I knew what it did. It was just a hidden carbon copy, but I couldn't think of a command.
See, this is the problem when we use acronyms for things. You start forgetting what they mean.
It doesn't matter if the word is synonymous with the meaning. Like, if I still know what it means, if I still knew that BCC meant it was going to CC you, but hidden.
All right, so you're in Final Jeopardy. There's 25,000.
happens.
There's
This is
25,000 riding on this.
I
Okay.
phone you.
You don't get phone a friend on Jeopardy. That's millionaire.
You're right. You're right.
Why do I know that? That's during your
I told you I wasn't going to make it there.
I mean, Who Wants to Be a Millionaire? That's like a recent-ish show, right? Like Jeopardy's been around since before you were born, probably, but Millionaire hasn't.
No, you're right.
Yeah, it's just crap, complete garbage. All right, so everybody, message me if definitely email Professor Locklear, but.
Like the whole email system's down. Oh, maybe not.
But carbon copy me on it so I can add you to my list of, because I'm going to be the one who's organizing the groups, and I'll be there the entire time for to help out with it and stuff like that.
Would it be possible to show up for the other half? Because I have to work in the morning. Would I still be able to get credit if I showed up at like 2?
Show up at 2 to 5. See, that's going to be tougher because the groups are already going to be.
Yeah, I would be like on the outside, but that's the only other way that I could get to work.
Well, don't you think you could? Can you find somebody?
I'll try.
All right.
If I absolutely can't find somebody,
Then we can talk.
Okay.
Perhaps between showing up late and.
If I get 5 points, I'd be happy with that too.
Well, I was thinking showing up. No, it's got to be an all or nothing thing. But maybe we could do an extra assignment or something. We could maybe figure something out. But the preference would be if you can't be there the whole time or close to the whole time, to find somebody who can contribute, so we can have enough people who are actually participating in the event. Leaving at something like 3 o'clock, that's fine. Because really you're probably there for a majority of the time, just not for the presentations.
So my friend can be contribute for you if you want.
Yeah, so if there's anybody in here who has people, this is kind of like human trafficking, I suppose, and you want to start selling your friends, we would prefer. So if there's a pecking order, computer science major or minor, IT major or minor, those would be the preference. Concordia student would be the next level down. And then if you can't have that, then an external entity would be acceptable, but the preference would be keep it within the department for the initial one, then within the university, then strangers, I guess.
Yes.
Right.
Most people you find.
If we already signed up with Professor Lockwood, do you want us to tell you that we're going?
Yeah, just email me so I can add you to my spreadsheet if that's cool. But since you're already signed up, that you won't get the extra credit.
Oh, I'm sorry, I didn't sign up.
You'll still get the credit. This jerk. All right, and that is a week from this Saturday. It's November 12th, from 8 a.m. until 5 p.m. Breakfast and lunch are provided. So I think there's gonna be bagels and stuff for breakfast.
What kind of bagels?
I'm not in charge.
Einstein's?
Huh?
Einstein's?
I would assume cream cheese. Yeah, I don't know.
Are these like store-bought bagels? They're probably the ones.
All I've heard is there'll be bagels. So who knows? But free food, so beggars can't be choosers, I suppose. And then lunch, I don't know what they're doing for lunch, but you won't have to pay for it. So it'll be free. I mean, for all I know, it's going to be like dog food or something. Like literally, you come up with a bowl.
Usually I don't get
It's like, dog food's usually heartier. It's got a higher meat content.
Oh, and organic. Nice.
And organic. Is it that Blues?
Yeah. Health or whatever.
Yeah. You know what commercials I love? I love the Friskies commercials with the cat. When he's introducing the kitten. You seen those? And yeah, so it's like it's the commercial. They make the animals talk. So it's like the older cat's like dear kitten. It's now that I've hissed at you the customary some zillion number of times. Now it's my turn to welcome you into the home or something. And he's introducing him to he's talking about the monster that sometimes comes around the house. It screams and eats at the same time, named Vacuum, and that kind of stuff. My favorite one is the one when he's introducing the kitten to the puppy. Let me tell you the type of intellect we're dealing with. This is an animal that, to determine whether it should put something in its mouth, it puts something in its mouth, and then it keeps it in. So it's that's the type of brain we're dealing with here. Those are great. It's Friskies commercials. It's all about getting wet food. It's the whole.
What channel is this?
I mean, they're all over YouTube. I mean, I've seen it on various channels. No, I mean, it's been on TV. But there's I think I've only seen maybe 2 or 3 different ones on TV, but there's 15 or 20 different ones on YouTube. Yeah, they're great. This is hilarious.
So you're watching cat commercials in your free time.
Right. Well, who doesn't? Who doesn't?
Mine are
Yeah,
commercials.
toxic, and you can use the curtains of invisibility to hide from vacuum. It's great. Plus, I think the voice actor who does the cat is somebody, I don't know who it is, but it's a voice you recognize. Kind of like the Arby's commercial guy is Darth Vader. Yeah. Although I've wondered if it actually is, or if the guy that sounds like
No
him.
way. It's voiced by Zay Frank.
Is that
He's
who?
a famous YouTuber guy.
Is it?
That's the guy I'm thinking of.
But I recognize the voice, so I don't know who it belongs to. It's actually an interesting question. I wonder if the Arby's voice is James Earl Jones, or if it's just somebody who sounds just like him. So since they don't show him, are they able to save a bunch of money having the consumer assume it's that of the famous person's voice? It's really an impersonator of the famous person.
That's what
It is?
Ving Rhames, everybody says he sounds exactly like James Earl Jones.
That's awesome. Money saving. Okay. Oh, we've been recording. Good. It's just gold. All that's going to be on the final, by the way. Okay. All right. So we so let's go this route. We'll call it gates, since we didn't have a quiz. Tell me what an AND gate looks like.
It's like a D.
It's a stretched out D, right? Okay, stretched out D is an AND gate. How many inputs to an AND gate? 2 inputs. How many outputs?
1.
1. Okay. So AND gate, we're going to call this guy stretched out D. All right. What about an OR gate? fish, arrow,
Sorry, it looks like a shield.
a sideways shield.
Yeah.
But that's more of a paladin shield, though, right? Yeah, kind of a sideways paladin shield. I assume everybody in here will know what that means.
It's more like a kite shield.
It's more like a what?
Kite shield?
A kite shield. Actually, that's not even true, is it?
Yeah, it is.
Wouldn't kite shields be a lot taller and
I'm going off of RuneScape knowledge from 2007, but
Oh, speaking of which, this is the actual quiz that you can answer as a group. So apparently there's a new Elder Scrolls. Is it actually a remake? It's the same game, just with better graphics?
It's Skyrim Remastered.
it's
Okay.
barely remastered.
It went from a 32-bit engine to a 64-bit.
Okay, has anything actually changed? Like, if you played the game before,
It could
do you have your same characters, or do you have to start over?
You have to start over.
Okay, but is it, you said it's, is it,
Can't you record your save if you didn't leave it? That's what
I thought you could.
is it worth playing?
If you like Skyrim.
I never played the original.
Oh my god, buy it. Buy it.
I know. I've heard so many good things about it. It was just, I think it came out around the same time as kind of an important WoW expansion, I think.
It takes some hours of your life.
I have plenty of time. I outsource all my programming now. So who cares?
Yeah, I would recommend that or Witcher 3. They're pretty comparable games.
Witcher 3?
You never heard of The Witcher?
No, I do know, but isn't that like more of a first-person shooter type game?
No.
Is it more like a Diablo game?
No. It's like a Skyrim game. It's like an open world RPG.
Oh.
That's kind of similar to
Sword.
But I hate open world.
That's what Skyrim is.
Really?
Yeah, Skyrim's open world.
Is there a goal? No, hold on. Is there a goal though?
For Witcher 3, yeah, you're.
Because I like, for instance, I didn't like Fallout 4.
Yeah, that one you're like, it's not really like you
Yeah,
have
if you
a.
didn't like Fallout 4, you're not gonna like Skyrim.
I don't think so.
Because Fallout 4, it was like too arbitrary. You know, there was a loose storyline, but if you got off the path even a little bit, you just lost your way.
Yeah, that's pretty much like Skyrim. Like I put like 300 hours into it and never beat the story. Never even touched the story.
But did you lose the story? Is that what happened? Like you couldn't get back? You like figured out like,
You could go back. It's just like there's so much other stuff.
well, that's what I mean, right?
You don't lose what person you have to talk to or whatever.
Right, but you can't find them. You forgot what town you last.
The quest system in Fallout 4 is much worse than in like Skyrim or Witcher 3. Skyrim, it's like it's just like you go here, like you select the quest that you're on, and there's like a main quest.
All right, so you would have to choose to get off path
Yeah,
for those. All right. And when does Witcher 3 come out?
it's already out.
And do I have to play Witcher 1 and Witcher 2 first?
No.
Should I play Witcher 1 and Witcher 2 first?
If you really want to understand the story.
It's like 50 hours per game if you want to like. I barely played Witcher 2. I played like half.
Well, can I just like pay one of you guys to play it for me?
Sure.
I could just give you my save.
IRL bot.
I don't use software bots anymore. I just hire humans. It's like the. All right.
That is internship credit.
Yeah,
pay.
internship credit.
It's just the internship credit to sit around and play video games.
It's research.
It's like, look, I'm getting a little concerned that somebody might message me in World of Warcraft while I'm, so I need you to just sit at the keyboard. If somebody talks to me, just act like a human. Like, what do you mean? I am a person. No, just act like a person.
I'll give you a set of prompts you can say.
Keybinds.
A friend of mine who I play World of Warcraft with, his mom sometimes plays in a group with us, and she was impressed how good of a healer I was. She was mentioning to me, he was at a wedding this last week, and then he told her that I cheat. It's a robot playing, you know.
Was she offended?
Yeah, apparently she was mad. It's like, well, you know, that's against the terms of service. And
That usually stops people when it's against the terms of service.
Yeah. I have a disability. I have a tremor in my left hand. Too much button smashing, and I can't even function. I mean, I would probably cheat. Would probably cheat anyways, but I do have a legitimate reason to kind of like hide behind. Is what I'm saying. All right, Orgate. So we're gonna say this guy looks like an arrow. Kind of like an arrow. Okay. So those are our. And then we have what, a not gate, or sometimes these guys are called inverters. Okay.
Circle.
So this is actually really an arrowhead, right? And this is a triangle with circle. Okay. What about a NAND gate? That's an AND with circle. What about a NOR gate? It's an OR with circle. Okay. What about a exclusive OR? So OR with line behind that guy. Okay, so all the exclusive stuff has the extra line behind it. All the not stuff has the circle after it. But our core symbol is either stretched out D or arrow. Make sense? Okay, and we all think we could do the truth table for those guys. We know what if the inputs for an AND is this, we know what the outputs would be. Okay, got it. So now, let's talk a little bit more about Skyrim. So, just teasing. All right, so we talk about adding bits. So if we have, let's put it in our truth table here. So we have 0, 0, 0, 1, 1, 0, 1, 1. So 0 plus 0 is what? 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0 with a 1 carry, right? So these are all 0 carries. That makes sense? So we have this tool called a half adder. Okay, actually, why don't we say this? We have tools called adders. These guys come in two flavors. We have a half adder and we have a full adder. Half adders have two inputs, two inputs, two outputs. 2 inputs, 2 outputs. So inputs are the 2 bits we're adding together. The outputs are the sum and the carry. Make sense? A full adder has 3 inputs and 2 outputs. Because a full adder takes in a carry. That make sense? So if we're looking at, so this guy right here, this is the half adder table. 2 inputs, 2 outputs. The C is just there to dictate that that guy's a carry. All right, 2 inputs, 2 outputs. That's half adder. Full adder zero plus 0 plus 0 is what? 0 with no carry. 0 plus 0 plus 1 is 0, is 1 with no carry. I'm going to steal this part so I don't have to keep typing it. 0 plus 1 plus 0 is 1 with no carry. 0 plus 1 plus 1 is what? Not quite. 0 with a carry, right? 1 plus 0 is 1 with no carry. 1 plus 0 plus 1 is 0 with a carry. 1 plus 1 plus 0 is 0 with a carry. 1 plus 1 plus 1 is what? 1 with a carry. So that's the truth table for a full adder. All right, so before we create those, to add binary numbers, so for instance, if we have the number 1, 0, 1, 1, and we want to add to that 0, 1, 1, 1, something like that. If we do that by hand, what are we actually doing? We're going through, we're saying 1 plus 1 is this, you do the carry, blah, blah, blah. But what if I want to build a machine that can add these two 4-bit numbers together? How would you do that? Yep, but I want the high level right now. I just introduced 2 new gates. You can treat these guys, full adders and half adders, as we'll call them super gates. We're going to build them in terms of their primitive types here in a second. I just want to give us some context of kind of why we're doing this. All right, so I can hand you a chip, and that chip is a half adder. That guy has 2 input ports and 2 output ports. Okay, I can hand you another chip, and that guy's a full adder that has 3 input ports and 2 output ports. So a full adder takes in a carry bit. A half adder does not take in a carry bit. Okay? So if we're looking at, where's my, it's weird that I had, there we go. Now we're back on right order. So if I have these 2 4-bit numbers, okay, and I say, I need a machine for adding 4-bit numbers. How would you add those together in terms of half adders and full adders? Where would you use a half adder here? Where is a half adder a good enough tool? Half adder is only taking 2 inputs, 2 bits, does not take in a carry. Where are we guaranteed not to have a carry? If I'm adding these, we add from right to left, right? So I do 1 plus 1, then I do this 1 plus 1 plus the carry, then I do 1 plus 0 plus the carry, 0 plus 1 plus the carry. The place, go ahead. Maybe I'm asking this in a crappy way. Would we ever have a carry when I'm adding those 2 guys together? Do I ever need to take a carry into consideration when I'm adding to 2 far right bits in 2 binary numbers? He might produce a carry. Yeah, he might produce a carry, but I never have to. I'll never have a magical carry that just appears up here, right? So I can use a half adder to add these far right bits. Okay, so if we kind of spell this out, we're going to have a half adder, 1 1. Okay, and that guy is going to have an output, right? So let's call this guy. Well, here. He's going to have an output that's going to go below, and the output in this case of that guy is going to be 1 plus 1 is a what? A 0 with a carry. Okay? Now, that carry, that's my 1 carry, is going to feed into a full adder. My full adder is going to take this 1 and 1 plus the carry of this guy. So here's my full adder, 1 comma 1, and then the result of that guy. Make sense? So the result of this half adder will produce the bit that is my answer here. In this case, that was a 0. But it will also produce a carry that becomes one of my 3 inputs into my full adder. That full adder will produce a carry. So there's my full adder. 0, 1, the result of this full adder. To add that, then we have a full adder 1, 0, the result of that full adder, to ultimately add these guys together, producing all the bits that would be down here. So that's going to be 0 is our first bit, then that's going to be a carry of 1. This is going to be a 1 with a carry, then this is going to be a 0 with a carry, then this is going to be a 0 also with a carry. 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry a 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. So I have an extra carry that's spilled off the end of this guy. Whoop. We'll call this guy an unused carry. Somebody else might use it, but this would effectively be an overflow bit. Does that make sense? Since we're doing 4-bit math, in this case I just arbitrarily picked 4 bits to make it complex enough for us to see kind of how this works, but not make it so long that I can't fit my adders all on one line. So it's kind of the appropriate level of complexity to, because you can imagine if we want to add 32-bit numbers together, we would do the exact same thing, wouldn't we? You would just have more adders. Make sense? Okay. So if we think about adders as primitive types, for the far right where we would never have a carry taken into consideration, we can use a half adder. So we can use a smaller machine. When we potentially need to take into consideration the carry bits, we would have to use full adders to pull that off. Okay. Now, again, it's kind of rolling back to last class, we introduced this idea of Legos, right? So our Legos are ORs, ANDs, NORs, NANDs, inverters or NOTs, and then exclusive of all those things. But realistically, our primitives are going to be AND, OR, XOR, or XOR, and then maybe a NAND or a NOR or something like that. And then the inverter is pretty important. But you can pretty much do everything with just ANDs, ORs, and in our world, and exclusive ORs with inverters. All right, so with that in mind, if we wanted to draw a half adder in terms of our primitive types, so you have a pile of Legos sitting in front of you, and you don't find a half adder Lego. Unfortunately, that guy was missing from the kit. All right, it's like, oh, you want a half adder? There. It's your half adder. Just look up your inputs. You're good to go. All right, so we don't have a half adder, so we're going to have a couple of inputs. So we'll call this guy A and B. All right. Then that feeds into our theoretical half adder. And that's going to output shouldn't those guys line up? No, whatever. That's going to be the output and the carry. That's what's going to come out of that. All right. So what I want to know is, how do we draw that guy? What's the guts of that half adder? This is our truth table for our half adder. Let's actually just translate that onto the screen here real quick. So truth table for half adder would be 0, 0, 0, 0. That's the output and the carry. This is 0, 1. I'll come back to that. 1, 0, 1, 1. So 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry. 1 plus 1 is 0 with a carry. All right, so I need a circuit that, given these two inputs, produces these two outputs. So what we've done now is we know that ultimately we're producing a half adder because we know that this is the truth table for a half adder. But at this point, when we're trying to solve this problem, all I'm saying to do is build a machine out of our primitive circuits that will produce that truth table. Make sense what I'm asking? Is it clear what we're trying to do now? All right, so I want us to take 5 minutes. I want everybody to work individually and try to create a circuit diagram for a half adder. That is, you have your two inputs, replace this guy right here with a series of AND gates, OR gates, XOR gates, NOTs, those primitive types to ultimately produce outputs that match the last 2 bits of this truth table down here. Make sense? And don't use the Google. Because you can look up on Google half adder and it'll show you your the symbols. Yeah.
No, it's
A, B,
two inputs and then
here's A and B, here's O and C. So this is your output, this is your carry.
Trying to get
So my advice would be forget that you are making something that adds something. Instead, use your primitive type Legos to build something that matches that truth table. I'm going to pause the up here. All right, so what did we come up with for our half adder piece here? What gives us this truth table? What pieces do we need? Okay, we need an exclusive OR. So let's take this, we'll drop it down here. Let's get rid of this. All right, so you want an XOR, and you said you also want an AND gate. All right, what do we feed into the XOR? A and B. Okay, and the output of the XOR gives us what? It gives us O. All right, so now before we do the other part, let's see where that matches up. So here's one of our outputs here, right? So an exclusive OR is true when exactly one of the input bits is true, right? So if we had taken out, let me steal this here real quick. If I only showed you that, that is the truth table for exclusive OR, right? So right off the bat, it tells you, I'm going to need an exclusive OR. We feed our 2 inputs, and that gives us our output. All right. Now let's flip that around, and let's do our 0, 0, 0, 1. Okay. What truth table is that? That's the AND, right? Okay, so this guy is only true when both inputs are true, and that gives us our carry. All right, so we hook both those guys up to the AND.
Could you just say whatever?
So what do I do? Well, first of all, is this accurate? Yeah, it's accurate. So does anybody have a different approach to it? There probably are other approaches. Remember, these are Legos. There's more than one way to build a castle. Right? So, you can get a similar truth table, but what we've tried to do here is we've tried to remove the idea of this being an adder and instead trying to match it up to a truth table. Dehumanize it, if you will, something like that. All right? So this guy is our half adder. Now, a full adder, so we kick over to this other screen here. Full adder guy. I'm going to steal this slide. A full adder has an extra carry here. It's an input. All right, so let's dump this for right now. All right, so didn't I already write it out for, I'll just write it again. All right, so those are our possible input scenarios, right, for a full adder. So A, B, and C, these are the possible A, B's, and C's we can have. All right, the output for these guys will be so for A, 0 plus 0 plus 0 is 0, 0 for output and carry. 0 plus 0 plus 1 is 1, 0. 0 plus 1 plus 0 is 1, 0. 0 plus 1 plus 1 is 0, 1. 1 plus 0 plus 0 is 1, 0. 1 plus 0 plus 1 is 0, 1. 1 plus 1 plus 0 is 0, 1. 1 plus 1 plus 1 is 1, 1. Right? Okay. So there's that guy. So now, let's dehumanize it. We have two truth tables we need to match. All right, there's one truth table. 3 inputs produces 1 output. Our other truth table all right, is that right? 1, 1, 1, 0, 1, 0, 0, 0. Okay. So this is our truth table for our carry. This is our truth table for our output. So how might we start creating this guy? So we dehumanized it, so we're looking at a kind of a design pattern, if you want, for creating circuits. Potentially, very likely, we're going to come up with a less than optimal circuit. Okay? But again, we just have Legos laying around, and we just need something that's correct. Once we have it correct, we can look at optimizing it, or we can just say, hey, this is good enough, and move on with life. Either one of those is a reasonable thing to do. All right, so let's focus in on just this guy first. Take that over to his own screen. All right, so I need a circuit that has 3 inputs and 1 output that produces this truth table. No longer, this isn't a full adder, I've dehumanized it. It's just I've de-circuitized it or whatever. This has nothing to do with adders. This just has to do with this one little truth table here, right? Because wouldn't it be reasonable for on a quiz or an exam or something like that for me just to give you a truth table and say, create a circuit that emulates this truth table? It doesn't have to do anything important. It could just match this truth table. This truth table just has meaning, right? So for us, here's a truth table. We have 3 inputs, A, B, and C, and 1 output. And we want the output to be this far right bit here. So when we look at this first, do we start seeing any patterns of what this guy might match up to? Say this again. Okay, so this top part here kind of feels exclusive-y, right? So if we look at, forget about this column right here. If we say this is A and B, these first two, so A's XOR, so 0, 0 is 0 for an XOR. 0, 0 is, hold on, I have this written wrong, don't I? No, we're right. Okay, so these are our A's. Let me rewrite. We're going to split this into 2 pieces. So we're going to further break down this truth table so we can see your XOR thing. You're right. Okay, so I'm going to further break this guy down. So we're going to deal with just A and B. Zero, 0, 0, 1, 1, 0, 1, 1. Okay, when that guy is 0, 0, we have a 0 there. That's one option. When we have a 0, 1, we have a 1. So we've marked this guy. We've marked this guy. We have a 1, 0, we have a 1. We've marked that guy. And when we have a 1, 1, we have a 0. All right, so those 4 inputs, only paying attention to the first 2 bits, the A and B, matches our XOR, correct? This is our XOR truth table. All right, so we can throw an XOR up here. Draw some lines. Okay, and this output that we're looking at here is related to our carry bit. Isn't that what this guy's related to? We have other carry bit issues to deal with here. We have another 4 patterns to deal with for our carry bit, but these guys, so 0, 0, 0, 0, 1, 1, 0, 1, I'm sorry, 1, 0, 1, 1, 1, 0, this is related to our carry bit output, correct? Okay. Or our output related to A and B here, since we've dehumanized this, I guess. So this is an output related to A and B. Okay, so now let's look at the other 4 things. So let's just copy this, put this kind of on the side here. So now let's look at some more of the bits. So let's look at A and C. When A is 0, and let's see, do we have a C is 0? We already used that one. So this is A and C, so 0, 1. We already have a 0, 1. Then we have a 1, 1. Okay, so those are our 2 for AC. and 0, 1 for AC should produce a 1, and 1, 1 for AC should produce a well, so we have a conflict between these guys, right? So it looks like we can't break it down that far. So we need to keep it at the 3 level. So we're going to have 0, 0. We've already handled all the things that have dashes next to them. So now we're going to do 0, 0, 1, 0, 1, 1, 1, 0, 1, and 1, 1, 1. Okay, like that. And the outputs for those guys should be 1, then 0, then 0, then 1. All right, so this takes into account A, B, and C. We might be able to further break just this piece down. So we've said we've already dealt with the guys with little dashes next to it up here, right? Okay, and we have an accurate output based on that. We don't need to do anything more with that. We just have to decide how we're going to label this output. But now we need to decide how do we use the other 3 bits to do something else. All right, so if we just look at this, now we can break this guy down. So let's just take the last piece off here. Actually, I'm lying. Let's take, we'll do A and B. Okay, and then, so let me label that so we don't start getting confused. This is A and B. And let me paste this in here. This is AC. And then I want to do one more just so we can look for a pattern. BC. Okay. All right. Do we see any patterns in those? A, B, A, C, B, C? Go ahead. Okay. So this is the inverse of exclusive OR. So 0, when they're both zeros, it's a 1. When only one is a, yeah, so typically exclusive OR would be these two guys are 1s, everything else is 0s, right? So this is not XOR. Fair enough. Let's put a little note underneath that. Not XOR or the equivalent, right? You know, we can do something maybe with a NOT gate and normal OR or something like that. Okay, but that guy looks like a not XOR. What about this guy? Same thing. When these two guys are, when there's exactly one, let's see where we at. No, it's not the same thing. Yeah, when there's exactly 1, 1, they flip. In fact, don't we have a conflict here? Okay, so what do you suspect we do when we see a conflict? Okay, so maybe throw that out because now we don't have a way of distinguishing the two inputs, right? So this guy should raise a red flag for us that given 2 inputs, we have 2 different outputs. And it's going to be very difficult for us to build a circuit that does that. We got to start getting into quantum computing and stuff like that for there to be different outputs for the same inputs. So we're not going to do that. All right, so let's not put anything underneath this guy. What about this guy over here? Same issue? Okay, so we have a not exclusive OR on A and B, but where does C play in here? How can we get C to play a role? I mean, the carry bit has to do something, right? Ah, so this is only half of our addition, right? So when I was doing our math over here, when I was saying, okay, it's 1 plus 1 plus 1, really we need to do the first two, and then we need to do the second two. So we can take another, here, I'm actually going to steal. Let me just steal the XOR first. So this XOR is going to take the output of that first addition, and then we're going to feed into it the extra bit that might change things, and that gets us our second half of our regular addition. Like that. Does that make sense? All right, so now, do we have our full output for the first three values of our full adder? So we have, for these first three values, we have all of these. But what about the carry? So now we need to have, if we have this guy, so we have this piece right here, right? That's our first output. So now let's backspace here, backspace here. Okay, so we have those three inputs we're still working with, A, B, and C. And then here's our output for our carry. So now we need a circuit that matches this, that takes into account potentially all A, B, and C. Because this is already our first output. We're good here. We have our half adder is, our full adder is done, except for the carry bit. So if we just decide to ignore the carry bit, we're completely done, right? But carry bit could be helpful because we just saw a little bit ago we created a 4-bit adder, for example, where we need that carry bit to feed into the next full adder. So how do I match up to this truth table? Go ahead. Okay, an and a NAND. Okay, how do you want to use the and? Start with the first part. Which bits lead up to an and here for you? Okay, top 4 only dealing with B and C. All right, so you're going to take that. We're going to dump A in this scenario. We're going to throw B and C. We're going to say B and C here just to remember what we're representing here. And this is an AND gate, right? 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. So we'll steal this guy here. We'll throw an AND gate there. And we want to hook up B and C to that AND gate. All right, so there's B and C to that AND gate. Now what? You said something about a NAND? So we've dealt with these top ones. You want to do B and C on the bottom?
Yeah.
All right, so B and C again. You have 1, 0, let's see, 1, 0, 0. It'd be easier just to write it all at once. Then 1, 1, 1. Then 1, 0, 1. Then 1, 1, 1. Huh? Instead of an and? Okay. So this is 1 or 0. Shouldn't that be a... Is this anything? What if we inverted any of these? Remember, we still have that magical inverter available to us that we can use to change the value. A 0 would become a 1 would become a 0. Okay, so if we inverted B here, this would be a bunch of zeros. So we'd have 0, 0 is 0, 0, 1 is a 1, 0, 0, still a 1. That's not going to help us. Say this again. Invert C. So this would be 1, 1 is a 0, 1, 0 is a 1, 1, 1 is a 1. Okay, actually, let's just do it. I confused myself here. So there's 1, there's 0, there's 1, there's 0. So 1, 1 is 0, 1, 0 is 1, 1, 1 is 1. Oh, we have a conflict. We're back to... maybe not B and C. Okay. You think you what? A and B? All right. So let's, I'll just write it again. So A and B is going to be for our bottom four, right? 1, 0, 0, 1, 0, 1. Uh-oh. What about A and C? 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So we have a match there. Does this guy look like anything to us? We don't have a conflict here.
1, 0, 0, 1.
Conflict here.
Yeah.
Yep.
So this is just impossible then.
Nah, it's not impossible.
Can we switch the XO and N?
You switch the who?
The XO on the top to the N to the top?
You could. But I think what we're going to find here is that we built in here, there's a couple ways we can do it. We actually have a half adder built in here.
Wait, is this a full adder?
We're on our way to a full adder.
Okay.
Yeah, on our way to a full adder.
Yeah, so it's just
All right.
a full adder.
So let's pause this here. I'm going to give you a, pop open the book here real quick. Let's see, we are starting. All right, in chapter 3, have we read the parallelism and SIMD stuff? By giving you assignments on that? All right, so why don't we do this? Finish reading chapter 3. I'm pretty sure we've gone up through division. I'm going to pick some questions from the end of the book, specifically dealing with parallelism and SIMD. So I'll give you maybe 3 or 4 questions to do over the weekend dealing with those two concepts. I might throw one of the other ones in if I see a good question, but those two concepts kind of finish off chapter 3 in terms of the difference between CPU level parallelism and hardware level parallelism, which then takes us into this next chapter. All right? Okay, I will see everybody on Tuesday.